All right, geometry, let's take a look at section 8.5. This is a little extra something that we like to do at the end of chapter 8 here. You're going to see more of this along with something called the law of cosines next year in Algebra 2. But it really seems a shame to me to have done this much work with trigonometry in chapter 8 here in geometry and not go ahead and kind of finish it up to its logical conclusion. The law of sines is really cool because it does one thing that we haven't been able to do in this entire chapter so far. And the important thing here is that the law of sines works in any triangle ABC. Everything we've done up until this point, the Pythagorean theorem, basic sine and cosine and tangent, special right triangles, angles of elevation and depression, everything we've done thus far has involved right triangles only. But the law of sines also works in acute and in obtuse triangles, and in addition to right triangles as well. Okay, so all of those work. Now, the law of sines is an equation here that says that in any triangle ABC, if you take the sine of one angle, like for example this angle up here is labeled angle A, and then divide the sine of that angle by the length of its opposite side, which we denote as little a, that ratio is going to be equal to the ratio of taking the sine of a second angle and dividing the sine of that angle by its opposite side, which is B. And furthermore, even though we don't usually do all three parts of it at once, that ratio there is equal to, here we go, the sine of the third angle now, angle C, divided by its opposite side, which is little c. Now this is a pretty useful piece of information to have in the arsenal then, everybody. We can use it to solve for missing sides in any triangle, not just in right triangles. I do want to take just a second and point out this convention right here. Most people know the Pythagorean theorem as a squared plus b squared is equal to c squared. And I should just point out that the convention here, that little c is always the hypotenuse, comes from this method that we've used within this triangle, that when you name an angle, that's a point, so you always use a capital letter for that, but then the opposite side across from that angle uses the same letter, but the lowercase variation of that. So side little a is always going to be across from angle big A. Side little b, right over here, is always going to be across from big B, and little c is across from big C. That always has to be the case, and if we don't understand that, then this equation here doesn't make a whole lot of sense. So we need to know that little a is going to be across from angle big A. So let's keep that in mind. This is the proof of the law of sines. Let me just walk you through it real quick, but if you want to skip this, no big deal. So I took a big triangle here, and technically this probably should have been triangle A, B, and a capital C. Oop, I hit the wrong thing. A capital C up there, but that really isn't important here. So here's angle A, and of course here's little a across from it. Here's angle big B and side little b across from it. And what I did is from point C, I dropped an altitude. And an altitude is a line segment that comes from a vertex in a triangle perpendicular to the opposite side. Now I didn't want to use A for that altitude because we're already using an A here, so I used H instead because it also represents the height of this triangle. And now what we've really done is we've taken this big triangle ABC and we've cut it up into two smaller triangles, each of which is a right triangle. So, just for simplicity's sake, let me call this point D right here. And I want to focus right now on triangle ACD. ACD. We have a triangle right here in yellow, and it's a right triangle. So we went ahead and we wrote out that the sine of angle A is, well, let's take a look, sine, if we recall from SOHCAHTOA, is opposite leg over hypotenuse. So from angle A, the opposite leg here is H, and the hypotenuse is B. Now, the same thing happens. I'm going to switch colors on you right here. And let's take a look now at triangle CDB. C to D and over to B, there's triangle CDB. That one is a right triangle as well. So when we go to take the sine of angle B right here, sine is opposite leg, which would be H, over hypotenuse, which is A. So these two statements here in blue come from two different triangles, but they're both equally true. Well, what you might notice is that these two equations have one term in common. They both have an H, and those H's refer to the same side right here meaning the h's are the same. So we're going to solve each equation here for h. I'm going to multiply this first equation by b on both sides. And the second equation, since they're dividing by a, I'm going to multiply by a on both sides. So here we are going to get, let's see, the b's cancel, and we're going to get h is equal to little b times the sine of angle A. And over here, these a's cancel, so we get h is equal to little a multiplied by the sine of angle B. Well, if h equals one thing, b sine of A, and h also equals a second thing, a sine of B, then by the transitive property, these two quantities here must be equal to each other. So we can now conclude that b times the sine of angle A must be equal to a times the sine of angle B, since they're both equal to h. So really, that's the magic right here that proves what we just did. But to get it in the format that we were looking for, we do something a little bit weird. What we're going to do is divide both sides of this equation by little a and little b multiplied together. Now we can do this as long as a and b are not 0, which they can't be because they're side lengths in a triangle. You can divide both sides of an equation by anything you want. And a cool thing happens here. On the left side, we have identical factors of little b on the top and the bottom that cancel. And on the right side, the identical factors of little a cancel out. So what does that leave us with then, everybody? We now have the sine of angle A divided by just little a is equal to the sine of angle B all divided by little b. And that is the first 2/3 of the law of sines. We could do all this again to get sine of b over b equals sine of c over c, but I think you probably get it. All right, as I said, that wasn't hugely important, but let's take a look now at how you can use the law of sines to find some missing information. Now, these directions here can be confusing if you haven't seen them before. When the directions simply tell you to solve a triangle, it means to find every single piece of information that isn't already given to you. Now, every triangle has 3 side lengths and 3 angle measures. That's a grand total of 6 measurements in every single triangle. And what you'll find is that in every problem that we give you, 3 of those 6 measurements are given to you. Here, you were given a 15 for the measure of what would really be side little b, because it's across from angle B. You were given a 72-degree angle for A and a 34-degree angle for B. So what I like to do here before I go any further is make a list of the things we're going to have to find. All right, we need to find the measure of angle C. That should be pretty easy. Then we need to come up with the measurement of little a, that's a side, and little c, that's a side as well. So those are the 3 things we need to know before we're done with this problem. Well, let's start off with the easy one right here. Angle C shouldn't take us much time at all. You were already given 2 angles within this triangle of 72 and 34 degrees, so to find angle C, we're just going to subtract those 2 numbers from 180. 72 and 34. So I'm going to take the total of 180 minus 72 degrees and minus 34 degrees. And that gets us an answer of 74 for this angle here. So with 72 and 34, we've now got 74 degrees for the measure of angle C. I'm going to go ahead and put that 74-degree angle right here in the figure. That's going to tell me something important, and in fact, let's talk about it right now. One of the big ideas from actually first semester that I'm hoping you guys remembered is called the triangle inequality theorem, and it says that in any particular triangle, the order of the side lengths is directly related to the order of the angle measures. I can see right now that angle C here is the largest of the 3 angles in this triangle. That means that little c here has to be the longest side. Angle B, right over here, the 34-degree angle, is the smallest angle, so this 15 has to be the shortest side. So I'm thinking ahead already. I know that A and C both have to be longer than 15, and I know that C has to be longer than A. So let's keep all that in mind. Okay, now the important thing here is this is not a right triangle. So using regular sine or cosine or tangent or the Pythagorean theorem, those aren't options. That's not really going to help us here. But we're going to need the law of sines. And to use the law of sines, what we're going to do is do sine of one angle divided by the opposite side equals the sine of a second angle divided by its opposite side. And what we really need to find first in order to start this thing off is one pair of letters here where we actually know the measure of the angle and the measure of its opposite side. I've got a 74-degree angle here, but I don't know the measure of C. That's not what I was looking for. I've got a 72-degree angle here, but I don't know the measure of A. That wasn't it. But right here, guys, we know that angle B is 34 degrees and that the length of its opposite side is 15. So angle B and side B is actually what I'm going to use to get this thing started. So I'm going to write here the sine of the angle that I know, which is 34 degrees, divided by the length of its opposite side, which is 15. So the sine of 34 degrees over 15 is equal to, and now you could really do this in either order that you wanted. I'm going to go with A first. Angle A has a measure of 72 degrees, and opposite from that 72-degree angle is side A. So that's what a setup looks like using the equation from the law of sines. It's a proportion, guys, a word we talked about at the beginning of chapter 7. Two ratios, or two fractions, set equal to each other. And the way we solve any proportion, is we cross multiply. And those two cross products have to be equal to each other. So again, I always like to do the one with the variable first. The A gets multiplied now by the sine of 34 degrees. And that product is equal to the product of 15 times the sine of 72 degrees. Now, I'm not going to my calculator here, guys. What I'd really like to do here first is get the variable by itself. So here's my variable, A. What's being done to it? It's being multiplied by the sine of 34. And how do we undo multiplication? We divide by whatever we were multiplying by. So we're going to divide both sides by the sine of 34 degrees. And as long as that number is not equal to 0, and it's not, we're fine. So the sine 34s on the left cancel each other out. And we're going to get A is equal to, and this can get just a little bit tricky to put in your calculator, so let me do it with you guys. 15 sine 72 over sine of 34. Okay, I'm going to use my stacked fraction button, and I'm going to type in 15 sine of, I believe that was a 72, let me check that, yes it was, divided by, I got to hit that there we go, divided by the sine of 34 degrees. Close that off and hit enter, and this now tells me that side A had a length of 25.51. Let me write that down, 25.51. Now, it's very difficult to verify this to find out if that answer is correct or not, but I'll go back to something I said just a moment ago. We knew that 34 degrees right here was the smallest angle in the entire figure, so that 15 had to be the shortest side. A and C both had to be bigger than 15. So I at least got that to work out. It doesn't guarantee that my answer is right, but if I got something less than 15, that would have guaranteed that I got it wrong. So I feel pretty good about that answer here. Okay, I'm going to do something here, guys. I'm going to take all of this work that we just did to come up with A, and let's see if I can slide all that down. Yeah, let's do that. And I'm going to switch colors on you now, and we're going to go to blue, and I'm going to do all this work again. Now, we are still going to use this same, by the way, I call this the peanut all the time, everybody. Kind of looks like that. The same angle here where you know the measure of the angle and the length of the opposite side. So I'm still going to begin this proportion with sine of 34 degrees over 15. But now, instead of focusing on angle A, now we're going to focus on angle C. So angle C is 74 degrees. So this is going to be the sine of 74 degrees all over little c, which is across from it. So this should look familiar. We still cross multiply here in this proportion, looking like that, and I like to do the variable first. So again, this is C times the sine of 34 degrees is equal to 15 multiplied by the sine of 74 degrees. And once again, C, our variable now, is being multiplied by the sine of 34 degrees. So we're going to divide both sides by the sine of 34, and that should get us what we need. Sine 34s cancel, we're going to get C equals, and remember everybody, the two things that we believe we know, C has to be bigger than 15, but C also needs to be bigger than the 25.51 we came up with. Since angle C is the biggest angle, little c better be the longest side. So this is the expression I now need to type in my calculator, very similar to the last one. So 15 sine 74 on the top. Got it. Close that off. And then from there, we need to put a sine of 34 degrees down there on the bottom. Okay, and we got 25.79 if we were going to the nearest hundredth. 25.79. All right, so if I write that here, let's make sure this works out the way we thought it to. We thought it would. We thought that C would be the biggest side, so bigger than the 15 and bigger than the 25.51, and it was, just barely. But actually, it's really interesting. If you take a look at these two angles here, the 74-degree angle and the 72-degree angle, those two angles are very, very close to one another. That means that sides A and C better be very, very close to each other in length. And sure enough, they are. Angle C is just a little bit bigger than angle A, which somehow I lost sight of. That goes right there. So side C should be just a little bit bigger than side A, and it is. So that's how you use the law of sines, everybody, to solve for a missing side within a triangle. And let's look at one case like this, which is a slightly different setup than what we had before. In the last problem, we were given two angles, and we were asked to come up then with, we were given two angles, and we were given one side length. Now, things are a little bit different. We're being given just one angle and two side lengths. So we need to come up with, let's take a look here. We need the measure of angle A, we need the measure of angle B, and we need the length of this side right up here on the top, which is going to be little a because it's across from angle A. So little a will go right here. Okay, so this one doesn't have the easy beginning that the last problem had where we just got to find a missing angle. So we're going to get rolling on this one right away and dive in with the law of sines. So here we go. Fraction is equal to fraction. And again, everybody, look for the peanut. Where is there an angle that we know the measure of where we also know the length of the opposite side? Well, the only angle we know the measure of is angle C right here. So our peanut encompasses that 108-degree angle, and that's 17 for a side length right there. So I'm going to begin my proportion with the sine of 108 degrees divided by its opposite side length, which is 17. And then from there, what I don't want to do right now, guys, don't write this down, but let me show you. I don't want to do the sine of angle A, because across from the sine of angle A is little a. Now this equation is technically correct, but there are two unknowns in that equation. We don't know the value of big A, we don't know the value of little a. So using the a's right here was not a good choice. We're not ready to do that just yet. Instead, we're now going to go with the sine of angle B. And this works better because we know the length of the side that's opposite from angle B. That side length is 13. So that's just one unknown, as opposed to what I set up a second ago that had two. Okay, guys, we are going to cross multiply here just like we did before to get 17 multiplied by the sine of angle B is equal to a 13 times the sine of 108 degrees. Again, I'm not going to my calculator just yet. This one is tougher because the variable in question is actually our angle, not just a side length. So how are we going to get B by itself? Well, we eventually need to get rid of that sine in front of it. But before that, what's happening to the sine of B is that it's being multiplied by 17. It's that 17 that we need to deal with first. So I'm going to divide both sides of this equation by 17. Those 17s cancel. And that's going to leave us now with the sine of angle B is equal to, and it's up to you guys right now. I would imagine that most of you would probably like to put this in your calculator and just deal with a decimal here rather than that big messy fraction. So that's what I'm going to do. I'm going to type in 13 sine 108 divided by 17. So let's see what we've got here. 13 times the sine of 108, close it off, and let's put all of that over, I think that was 17, I should double check that. 13 sine 108. Sine 108 over 17. That got me this decimal of 0.727. Now, if you do this right, it doesn't really matter what you write down on your paper. 0.727. All right, and I should have left some room here. Here's why. We now need to get this b by itself, which means we have to undo this sign, which we're going to do by taking an inverse sign on both sides. Now, what I'm about to tell you here is always important, you guys, if you want your answers to be accurate, but it's especially important when we're doing trig. The inverse sign and sign cancel, so we're going to get capital B is equal to, and it's the inverse sign of this number, but it's important that everybody recognizes that this number here, 0.727, is not an exact value. It's not exactly 0.727, that's an approximation. So we want to do the inverse sign of that last answer in our calculator. So what I'm going to type in here is inverse sign, and then this calculator that I'm using has a button right underneath my 3 that says ANS. Now on your Texas Instruments calculators, usually what you hit here is the second button and then the equals button. And that'll get you, the second button and then the negative button. But when I do that, it takes the last answer exactly, not rounded, the exact value of it, and plugs it in. So this is a more accurate answer than I would have gotten if I had just typed in inverse sine of 0.727. So it looks like this angle in question, angle B, is 46.66 degrees, everybody. So let me write that down for B, 46.66 degrees, and I'll put that here as well, 46.66 degrees. Okay, that was fun. All right, all of that work was to find the first thing we needed right here, which was the measure of angle B. So let me try to take all of this work here, or at least as much of it. No, I don't want that to go. And let me just see if I can slide all of this down and out of the way. That parentheses no good to me now, so I'm going to get rid of that. All right, what are we going to do next? Well, now that we know two angle measures, angle C is 108, and we know angle B here as well, we should be able to figure out angle A. So to find A, we're going to take 180 degrees, which is the sum of all three in our triangle, and subtract the two angles that we know. Angle C was 108, and we just found that angle B was 46.66. Rounded anyway, I should say. So, calculator time again, and here we go. We are going to take 180 minus the 108 we were given, and minus, now again, I don't want to type in a rounded decimal, so I'm going to hit last answer, and this tells me that angle A now is 25.34 degrees. All right, so A is 25.34 degrees, and we'll put that right here. And now that we know the measure of angle A right here, now we can go back to what we were going to do a few minutes ago, and we can set up another law of sines equation, this time trying to find side A. So I begin just like I did before, with the sine of 108. I always use my peanut first. The sine of 108 divided by 17. And that's now going to equal the sine of angle A, and we now know that angle A is 25.34 degrees, all divided by little a. And there's our proportion. So now we're going to cross multiply. The A gets multiplied by the sine of 108 degrees, and that equals 17 multiplied by the sine of 25.34 degrees. And to get A by itself, it's being multiplied right now by the sine of 108, so we're going to divide both sides by the sine of 108. And this is going to be messy and complicated to do in the calculator, but it's going to work. So we're going to get little a is equal to, and the tricky thing here, guys, that 25.34, once again, is an approximation. So instead of typing in 25.34, I'm going to use my last answer key. All right, so what do we need here, everybody? We need a stacked fraction. We need a 17 times the sine of the last answer, 25.34, blah, blah, blah. 17 times the sine of that divided by the sine of 108 degrees. And that gets us an A value of 7.65. So let's write that down, 7.65. Let me box that up, and let me see if it makes sense. 7.65. So we think that these are our three answers to this problem. Let's make sure about something real quick. Is the longest side across from the biggest angle? Well, the biggest angle is C with the 108, and that 17 was longer than 13 and longer than what we came up with for A. So that makes sense. Next, is the shortest side across from the smallest angle? Well, my shortest side is A, which ended up being 7.65. Is angle A the smallest angle? Well, again, looking at A and B and then angle C right here, yeah, angle A is the smallest angle. So again, that doesn't guarantee that we got this problem right, but if that didn't work out correctly, it would guarantee that we got the problem wrong. So that's always a good thing to check at the end of a section. Okay, so if you didn't think this was too bad and you're so inclined, go ahead and give the 8.5 homework a try, and let me know if you guys have any questions.